Okay, now I just wanted to go through heat transfer right here, and which is the second chapter on that section on heat. We're only going to do 2 sections there. And when we move heat from one spot to another, transfer energy from one spot to another, there's just 3 ways of moving heat around. One of them is by conduction. Conduction. Well, what would be an example of conduction? Well, if I have, let's say, a bar of steel right here, steel, and I put this end under a flame right here. What do these atoms do? They're going to start moving around faster and faster. They're going to jiggle their neighbors. They're going to jiggle their neighbors. They're going to jiggle their neighbors all the way down. And then pretty soon this end's going to start to feel hot. So you've moved this heat this way. Pretty soon you can't even hold this any longer right here. Steel is anything that would transfer pretty easy. We would call that a good heat conductor right here. If you had a piece of wood, if this were wood, this could be on fire and you could hold this end. Heat does not transfer through wood very easily right here. So wood would be a poor conductor of heat right here. This comes up a lot of places right here. Water is actually a good conductor of heat. You notice if you jump into a swimming pool and the swimming pool is at 70 degrees, you would say, boy, that's cold. It's not cool, that's cold. 70-degree water, pool water's cool. But 70-degree air feels nice right here. And that's because water's a good conductor. Air is a very poor conductor right here. Air doesn't transfer heat very well right here. And so that's why if you have something like a down coat, what's in a down coat? Feathers. Well, what is it that keeps you warm? Is it the feathers or the space between the feathers? It's actually the space between the feathers that keep you warm right here. So it looks like a blow-up coat would keep you pretty warm, except that's probably not good because you might have a leak in your coat right here. So if we look at something like what we use to keep the house warm, we use fiberglass. Well, it's not the glass in the fiberglass that keeps the house insulated. It's the space in between. If you look at fiberglass, it's kind of real puffy and stuff. It's just the space in between that keeps your house insulated. It's not the material. And so if we look at something like an igloo, they're quite insulated right here. The Eskimos don't freeze in their igloo right here. It gets quite warm in there. It's because ice right here has all those little voids in it, we said last time. And the little voids is a gap, an air gap, and so all that little air spaces gives you good insulation right there. So there is some pieces of conduction right here. If we've ever, I don't know if we don't live in cold country, but you've probably seen movies where someone licks a flagpole in the wintertime and their tongue sticks to it. Well, that's because if the flagpole is such a good conductor, as soon as you touch your tongue to it, you freeze. Your tongue freezes onto it right there. It sticks right here. Now, you could lick all the wood trees you want, but you can't lick steel out there. Otherwise, your tongue's going to stick to it right there. So this is all conduction right here. So that's one way you can move around heat. The second way of moving around heat is called convection. Convection is where the material actually moves. Here, you notice the steel didn't move. We just shook their neighbors, and pretty soon this end got hot right here. But suppose we heated up this bar and threw it across the room. Then we're moving it around through convection. We usually don't throw around hot bars. We usually throw around hot air. So if you got air going this way, hot air, it's usually the way we move it around by convection. You might have a heat source and a fan or something, and we can just blow hot air around. That would be convection right there. Now with convection, first of all, we have hot air. Hot air it likes to rise. That's why a hot air balloon wants to go up right here. Why does hot air want to go up right here? The only difference between hot air and cooler air is the speed of the atom. So let me look at an analogy. Suppose you're at a party or something and there's a band playing, and here's all the band members playing on the stage right here, and all the people at this event right here, most of them are going to be close to the band right here. They're all really close to the band. The further away you get, the more spaced out they are right here. In the back of the room, they're pretty far spaced out, but they get close, they're a lot closer. Now, let's say you've got someone that comes and he's been drinking too much. And so let's say you plop him right there. He's been drinking and he's quite obnoxious, so everyone wants to get him away, so everyone's pushing him. If everyone pushes him, then he's kind of bouncing off people right there. You notice every time he gets pushed this way, there's less people, and he goes a little bit further. Every time he gets pushed this way, there's more people. So what's going to happen if he's just bouncing around people? He's going to actually work his way up here, and you'll notice all the drunks stack in the back of the room at the end of the day right here. This is exactly the way the atmosphere is. Air atoms are a lot closer down to here, down to the ground. This is the earth, and then you go up. If you introduce a hot air atom, it's bouncing around, and every time it goes this way, it's going to run into more than going that way, and so it kind of diffuses its way up right here. So hot air likes to rise right there. So that's why my hot air balloons, again, like to rise right there. Now, what about expanding air? Suppose I have, we'll put it in a container right here. We got air, hot, could be any gas. We have hot air in here. And now we expand it out. Now we're going to just move the walls away right here. Move them outward right here. Well, anytime these atoms run into a wall that's moving away from it, it's going to slow them down. It's kind of like if you rear end someone in your car is always going to slow down right here. You're never going to speed up if you rear end someone that's moving away from you. So it's going to slow these things down as long as the wall's moving away from you. So expand, it doesn't even have to be a wall. They could run into an atom in front of them right here. If the atom's going away from them, they're always going to slow down. So expanding air cools. Slows down, so that cools. And you can test that out. Let the air out of your bike tire, feel the air coming out. It feels cold. It's not cold in there. It's only cold because it's expanding. Even if you just blow into your hand like that, my hand feels cool. The air feels cool. If I don't allow it to expand, it doesn't feel cold. So you want it to, anytime air expands, it's going to cool. The opposite, compressing air, if the walls came in and you hit a wall coming at you, you're going to speed up. So compressing the air heats it up. Compressing air warms. If you've ever felt a bicycle pump after you pumped up your tires, you pushed in there, it feels warm right there. Just the pump would feel warm. So compressing air warms, expanding air cools right there. Okay. And rising hot air rises right here. So now that we have these, you'll notice if you go down to the beach, let's say this is the sand coming down, here's the sand, here's the water, the waves coming in right here. You'll notice that in the middle of the day, it's usually windy. When people fly kites, it's not in the morning or in the evening, it's in the middle of the day. Why is it you usually get a wind right in the middle of the day at the beach? Well, it's because, first of all, sand is a low specific heat. Low specific heat means it gets hot. In the middle of the day, this sand gets hot, which means this air is hot right here, right above it. Hot air rises. So this hot air goes up. I need new air. Where do I get new air from? It comes in from the ocean right here. And when this hot air rises, it expands. Expanding air cools, so this thing cools. And what you get is you get a little, it's called the convection current that goes around. It comes inshore, goes up, comes around. That's why you fly the kite right around here in the middle of the day. So you're always going to get this little breeze coming in off the shore, coming in from the ocean inward right here. You'll notice if you go down in the evening time or early morning, the sand and the ocean are pretty much the same temperature. If they're the same temperature, you're not going to get this going on right here. So it's really going to work best when it's really hot right there. We call these convection currents right there. Okay, so there is just convection right there. And then the third way of moving around heat is called radiation. What's radiation? Radiation is light right here. You can heat up things with light. So if this is the ground, when light comes in and hits the ground right here, what's going to happen? Well, it can either reflect, or it can come in, absorb, and re-emit. So now it absorbs and re-emits. Now you might say that looks the same as this, but it's not quite the same right here. This one, it doesn't lose any energy on the surface. So the energy of this is the same as the energy of this. We would call this something like a white surface. A white surface. So a white surface doesn't lose much energy, and that's why if you're ever walking barefoot on a parking lot in the summertime, you're always walking along that white line. You touch that black part of the surface and it's going to burn your feet. So here, whenever light hits a white surface, it just reflects and there's no energy lost on the surface. The opposite of that would be light coming in and hitting a black surface right there. Now the light gets completely absorbed and then it re-radiates right here. But we can't see this radiation because it's not in the it's not in the part of the spectrum our eyes can see. This would be in the infrared part of the spectrum. We can't see it, that's why it looks black to us. Our eyes don't pick up. If we could see infrared, this wouldn't be black right here, but we can't see it right here. And so this thing right here, since there's energy absorbed right here, this surface is going to get hot right here. And so the black surface is going to get hot when you shine light on it. White surfaces won't get that hot right here. Now the rule is, if you're good at this, you're poor at this. If you're 50% of this, then this is the other 50%. If you're like gray or something, you reflect part of it and you absorb part of it right here. But the two are exclusive right here. The better you are at one, the worse you are at the other. And also, the better you are at absorbing, the better you are at emitting. These two go together right there. So now, if you have, if we look at your car right here, let's say you park your car in the parking lot in the summertime right here. Now, hopefully you got a newer looking car than this, but what do we got right here? Here's the front end of the car right there. You'll notice you park the car, you get out, you go into the store, 5 minutes later you come back. It's hot in there. It's like the temperature of the sun in there, it seems like, right? How come it gets so hot in there in such a short period of time right there? Well, what do we have? We have, first of all, we have windows right here. Now you have windows around the sides and the bottom, but let's just look at here. You got windows, you got light. The nice thing about windows is white light goes right through windows right here. And so light can get inside the car very easily. Now, what happens when the white light, or the light, hits your black velvet, sorry, not velvet, hopefully you don't have velvet seats, but black leather seats. Here you got some black leather seats right there. Well, black absorbs the light and re-emits in the form of infrared right here. Infrared right there. I'll have to draw it in blue. Infrared comes off. Now, infrared can't get through glass. So it's now trapped in the car right here. It's trapped. And so what is your car now? An infrared factory right here. And what does infrared do when it hits your skin? It shakes the molecules and we feel it as heat right here. So this is like a heat. It's just creating more and more heat in there, creating all this infrared right there. How can you keep that to a minimum? Well, you can allow this blue infrared to get out. You keep the windows down, but that's probably not a good idea. You could put those shades in front of the windshield right there to try to keep the light from coming in right there. There's another way you could do it. But, you know, it's not going to help. You could put the shade there, but if the sun is over here, you know, you're going to have to put it on the back window right there. So you should always, when you park your car, look to see where the sun is, because that'll tell you which shade, where to put the shade on your car right here. Now, if you see a shady spot, do you want to park at the shady spot or the one next to the shady spot? You want to park at the one next to the shady spot so it's shady when you get back. So it's a big procedure to find out where the sun is so that you can at least minimize this heat when you get back to your car right there. So this is actually what happens on the surface of Venus. On the surface of Venus, their atmosphere can allow optical light through the atmosphere. They have a lot of CO2 in the atmosphere, which holds the infrared in, and the temperature on Venus is like 900 degrees Fahrenheit. That's hotter than your oven in self-cleaning mode. So that's why we don't want to put too much carbon in our atmosphere. Otherwise, we'll have that same sort of problem right here. So there is your car. If we look at, sometimes you'll notice in the morning, on a cold morning, if you look at the grass, you're going to see frost on the grass. Or sometimes you even see it in your car. You see frost on your car, yet you say it wasn't freezing that night. How do you get frost on the grass or on the car when it wasn't freezing? Well, normally on your grass, you have, in the daytime, you got radiation hitting it, warms up the grass. And you have wind blowing here, which can also move around heat, the wind. You don't get very much heat from the ground because dirt is a pretty poor conductor right here. Well, we'll suppose at nighttime. Nighttime, you don't get any light from here. You don't, if it's not windy, you don't get any from here. And you don't get any from here because dirt's a poor conductor. So you have no way of getting heat to your grass. But your grass is always going to be radiating because the atoms are shaking. All shaking atoms radiate. It's just that now you're radiating more than you're getting. And so the temperature of the grass can actually get below freezing, even though the temperature is well above freezing right there. And so this comes up this way, get the frost on the grass. Now, if we look at the sun, last thing right here, if we look at the sun generates a lot of heat. It's all right at the core. So the sun, here's the core of the sun. Sun goes all the way out to here. But this is where all the fusion is going on right here. And this is where all the heat is generating. It keeps generating it. You got to get rid of that heat, otherwise the temperature is just going to keep growing. So heat has to get out of the core of the sun. So it goes out this way. And, well, how does it get from the core out to the edge? Well, it's got to go by one of these three right here. That's the only three you have. And it just so happens that it picks this one right here, radiation. If I could follow one little particle of light coming out, it kind of bounces around just like at the band when we were talking about the faster moving air. Here you got a photon, they just bounces of light, bounces around. It takes about 1 million years for that light to get near the surface right here. Now, and as we keep going out further, the temperature is dropping. Here it's probably about 15 million degrees. It drops, drops, drops. Right about there, it's about 6,000 degrees Kelvin. And once it gets to 6,000 degrees, it says, you know, that last little bit, I'll get there by convection. And it'll be just like this right here with the ocean. And we get these little convection currents right there, where hot gas comes up, cold air goes, colder gas comes back down. Cooler gas is a little dark spot. Brighter gas is a little hot spot. And if you look very close at the sun, you have to look pretty close with a telescope, what you'll see is bright and dark spots all over the surface. It's called solar granulation. Where the hot gas comes up, it's a little brighter. Where it goes down, it's a little darker. So it covers the whole surface right there. Now, those aren't the sunspots. Sunspots are completely different. They're big spots, and that's where you have a magnetic field, and that stops the convection right here, and so that's why it gets a little darker right there. And if you ever break that, that's what gives us our solar flares right here. So now we've got heat to the surface. Now it's got to get to the Earth. Here's the Earth over here. How does the heat get from the sun to the Earth? Well, it comes by radiation again. So here we got light coming in, hits the Earth right there, heats up the surface of the Earth. We got winds blowing it around to kind of evenly distribute it. If we didn't have winds blowing it around, this temperature would really be cold at night, really be cold. Luckily, we got winds that kind of distribute this. And whatever heat we get from the sun, we better be the same amount that we give back off. If it's not true, then we're going to heat up. And that's what's happening now. With global climate change, we get more energy than that's coming out, and so it just raises this. If we could get more out than coming in, we'd be heading toward an ice age. So what you'd like to do is balance all this stuff out right here. So whatever we get coming in is the same as we got going out right there. Okay, so I think I talked about this is just 3 ways of transferring heat, and these are the 3 ways. Okay.